Hey everyone, welcome back. Here is lesson 4 of unit 1. In this lesson, we're going to talk about limits as x approaches infinity. And the idea is really the idea of a horizontal asymptote, because that's essentially what the definition of a horizontal asymptote is. So just kind of give you an idea of what this looks like. If I just look at a line, and I think we're going to do that in just a second here. In fact, let me go ahead and bring up this first one. It says, what is the limit as x approaches infinity of 2x plus 1? Well, that's like saying let f of x equal 2x plus 1. And we're taking the limit as x approaches infinity. Well, remember, infinity is not an actual number. It's just an idea. But it's the idea that we are getting further and further and further out there. In this case, we're moving further and further and further to the right. X is getting bigger and bigger and bigger. So, graphically, we can see this. What is the y value approaching as x gets bigger and bigger and bigger? Well, we got the graph of the line. Essentially, that's what it is. The y-intercept of 1, slope of 2, a little off scale, but that's okay. As x gets bigger and bigger and bigger, the y value is getting bigger and bigger and bigger and bigger. And so we can say the answer is infinity. And we can look at that graphically to try and understand it. But analytically, remember, what do we do to find a limit? The very first thing we do is we substitute. Well, let's go ahead and substitute here. We would end up with 2 times infinity plus 1. You go, what? 2 times infinity? I thought you said infinity's not a number, it's just an idea. It is the idea of a really big number, in a way. So what is 2 times a really, really, really big number? Well, it's an even bigger number. And so when I take an even bigger number and add 1, I get an even bigger number. And so this ends up being a really, really big number, which we refer to as infinity. And so we can say the limit as x approaches infinity of f of x is infinity, both graphically and analytically. Okay? So again, substitution is so important. Okay? We also say this, and this is really important. Whenever you get an infinity out as a limit, then we also say and does not exist. Because again, infinity is not a specific value. And you can see it's not a specific value because this infinity, in a way, is a different size than that infinity, because we're multiplying that one by 2 and adding 1. So it's not approaching a specific infinity. So we say does not exist. Anytime you get plus or minus infinity, you say plus or minus infinity, whatever it is, and does not exist. You have to put both statements in to make it correct. So again, infinity and does not exist. By the way, this is my notation. It's probably not a good idea to say DNE. You should be writing out does not exist. Okay? All right, let's go ahead and take a look at something that may be a little bit more difficult. Okay? Kind of interesting to talk about here. What happens when a fraction's numerator increases while its denominator stays the same? Well, what does that mean? The numerator increases while the denominator stays the same. So I'm going to go through an experiment with you. If the denominator is staying the same, let's just say the denominator is 8. And that stays the same as we look at a sequence of numbers. Okay? Let's say we start out at 16. And what's happening to, sorry, the numerator is increasing. So I'm going to go the other way, actually. Let's say we start out at 1, and we go to 2, and we go to 4, and we go to 8, we go to 16. What is happening as the numerator increases, but the denominator stays the same? What's happening to the overall number? Well, 1/8 is, what is that? That's 0.125, I believe. Okay. 2/8 is 1/4, so that's 0.25. 4/8 is a half, so that's 0.5. 8/8 is 1. 16/8 is 2. So we can see something happening here. Let's keep going. Let's make this bigger and bigger and bigger. Let's say this is 48/8. Let's say it's 80/8. Let's say it's 8,000/8. Or 8 million. What is that? 8 million/8. What do each of these, what happens here? We got 48 divided by 8 is 6, 80 divided by 8 is 10, 8,000 divided by 8 is 1,000, 8 million divided by 8 is 1,000,000, okay? So we can see as the numerator gets smaller and smaller and smaller, but the denominator stays the same, the overall answer is getting bigger and bigger and bigger. So I use 2 as my denominator in this example. And so as the numerator gets bigger and bigger and bigger, we got 0.5, 1, 1.5, 50, 250, in this case 50,000. As it gets bigger and bigger and bigger, the numerator gets bigger, we see that the answer gets bigger and bigger and bigger. So the resulting answer approaches infinity. If I keep adding zeros, I'll keep adding zeros. So I'm approaching infinity. Okay? So we can say this, and this is very important. The limit as x approaches infinity of x over a, okay, where a is greater than 0, where a is essentially a positive number, that's infinity. Well, why is that? We're saying a is just a constant value that's positive. It's not 0. That would cause us problems in a sense, but it's not 0. It is a positive number, and it's staying the same. So just like this is staying the same, and the numerator is getting bigger and bigger and bigger because x is approaching infinity. If you see that, then you get infinity. Whereas the limit as x approaches infinity, negative infinity it says, of x over a, where a is greater than 0. Okay, you can see that here, but keep in mind, now we have a constant value that's still greater than 0, still positive, but now we're going that way. We're going as x approaches negative infinity. But still, think of any number. In a sense, the numeric value is increasing, but it's negative, right? So we can just basically say, okay, x is negative, so this is going to be the same as saying the limit as x approaches positive infinity of negative x over a. Because I took the negative out, so I took the negative out there. But the bottom line is, since this one was positive infinity, this one's going to be negative infinity. And just to emphasize that, if this is negative, as it's approaching negative infinity, all that's happening is that these become negative values. And therefore, you get negative infinity out of it. Okay? Here's another look at it. Okay, and again, because we get infinity or negative infinity, we also say does not exist. Here's another concept. Okay, here's something else I want you to consider. What happens if the reciprocal function? In other words, as the denominator gets bigger, as the denominator gets bigger, but the top stays the same. So let's say this is 8 over 1, 8 over 2, 8 over 4, 8 over 8, 8 over 16, 8 over, let's say, 80, 8 over 800, 8 over 8,000, and so on. Okay? What happens when the numerator stays the same and the denominator gets bigger? Well, we get 8 and 4 and 2 and 1 and 1/2 and 1/10 and 1/100th and 1/1000th. So what's happening to these? In other words, this is 0.1, 0.01, 0.001. If I keep adding zeros, go on forever if you want, because that's the idea, we're going to get 0.0000000000001 or whatever it is, right? And don't count me on that. I didn't count the zeros. But the idea is, what is the value approaching? It's approaching 0. It's getting really close to 0. So as a result, we can conclude that the limit as x approaches infinity of a over x is 0. Okay? So let's take a look at that. The result is approaching 0. So the limit as x approaches infinity of a over x is 0. And in fact, it doesn't matter whether a is positive or negative. I didn't have to put a clarification here. And in fact, a could be 0 because 0 divided by anything is 0, right? So if I were to put a negative a value, what happens? Well, that's negative, 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 but it's still approaching 0. It's just approaching it from underneath instead of above. Okay? So that's important. And the limit as x approaches negative infinity is also 0. So the limit as x approaches negative infinity of a over x is also 0. Because, let's say, we throw negatives on the bottom now. As x approaches negative infinity, as x gets really, really small, really, really negative, these are still going to be negative values, but they're still approaching 0 there. So this is something that you really need to kind of conceptualize and understand, that as the denominator gets bigger and bigger and bigger, you get infinity. As the numerator, sorry, I said that backwards. If the numerator gets bigger and bigger and bigger, you get infinity. If the denominator gets bigger and bigger and bigger, you get 0. Okay? So pay attention to the limit notation of that. Okay? This is something that I often find myself repeating. So if you have questions, make sure you're asking me. Don't just let it go by the wayside. So let's take a look at a practice problem that is dealing with this idea and see what we come up with. We're looking for the limit as x approaches negative infinity of x squared minus 5x all over x. Now remember, always substitute first. So we try substitution. We get infinity squared minus 5 times infinity all over infinity. Well, infinity squared is infinity. Minus 5 times infinity is infinity over infinity. You go, well, okay, what's infinity minus infinity? It's not 0 unless those infinities are the same. Here's kind of a clue. Infinity squared, a number squared, grows faster than when I take a number and multiply it by 5. So this number is growing more than this number is, which means when I subtract them, I'll ultimately get a positive number, and a really big positive number. So really what this is infinity over infinity. Now remember from previous lessons I said this is the other indeterminate form. Okay? And again, here's why. Because if you looked at the last slide, as the numerator gets bigger and bigger and bigger and bigger, so again, infinity over some constant should give you infinity. Okay? But if you have a constant over infinity, you should be getting 0. If the numerator gets bigger, you get a bigger number. If the denominator is bigger, you get 0. So this thing is telling me it's getting really big, and this one's telling me it's getting really small. Those contradict each other. That doesn't mean there's no answer. It just means we don't know the answer yet. So we have that. Well, what's our next step here? Our next step, we could try maybe factoring. Factoring is always good. So this would be the limit as x approaches infinity. If I can factor out an x from the top. And look at that. Those x's reduce. And now I can plug in, I can substitute that infinity. And so I end up with infinity minus 5. And so that would be infinity. Or we also say does not exist. Okay? So really important stuff. Really important stuff. We need to understand how to get negative infinity out of that. That's interesting. Oh, I didn't see that. That's a negative infinity there. Okay, so that's negative infinity and negative infinity. So that's a positive. Negative 5 times negative infinity is positive infinity, which still gives you infinity, essentially. And then this is negative infinity. So this, when I substitute, is negative infinity, and negative infinity minus 5 is negative infinity. But still does not exist. This is what you need to grasp from this right now. When the top is infinity, the result should be infinity. When the bottom is infinity, the result should be 0. If they're both infinity, you got to do something else. Okay? All right, let's go ahead and take a look at the next idea of infinite limits. Let's see what we got here. You guys go ahead. Oh, here's another example. I'm gonna walk you through this one because this one might not be so obvious. The limit as x approaches infinity of x squared minus 5x minus 6 all over 2x squared plus 7x minus 4. Okay, well, what do we do? What do we do? We substitute. We try substituting. Infinity squared minus 5 times infinity minus 6 is going to be infinity. Infinity squared times 2, that's infinity, plus infinity minus 4 is infinity. We have infinity over infinity, indeterminate. And I just flew through that for the sake of time, but you should still show the work for it. Okay? So it's indeterminate. So what's our next step? Well, let's try factoring. The limit as x approaches infinity of x, let's say 6 and 1 is the correct factors there. And then on the bottom, we have a factor that has a 2x in it and an x on the other one. We know that that's going to be, 4 and 1. And that's going to be positive and negative. So those are my factors there. So I've got factors, I got x minus 6 times x plus 1 and 2x minus 1 times x plus 4. Uh-oh, nothing reduces. So factoring doesn't work in this case. What could I do to help me see this? Okay, so we tried substitution. It gave us infinity over infinity. That's indeterminate. We tried factoring, and we could factor, but nothing reduced, so that didn't help. What could we do? Well, why don't we try using our calculators to determine a tabular method? Let's look at it through tabular means. So we are looking for as x approaches infinity. So if I was to create a table, and I'll just call this f of x, what x values would you be plugging in to get closer and closer to infinity? Well, maybe I'll start out with 10, then I'll go on to 100, and then 1,000, and then maybe 10,000, and then maybe 100,000. Okay? It's kind of important that you don't use linear increments, that you don't go 10, 20, 30, 40, 50, and you go, well, why not? It's increasing to infinity. Yes, but you're keeping this a pattern, so you might see a pattern here that is not showing what really is going on. So we're trying to get to infinity, so we kind of got to get there. We don't want to just plug in 100,000 and say, oh, that's getting really close to this number, so it's a limit, but we want to see it progress. So remember, in your calculator, we type this into our Y list. And then we go to the table set, so that's the green F4 button. We want to change that to ask if you don't have it already, save it, and then go to the table, which is the green F5 button, and just start plugging these x values in. So 10, 100, 1,000, 10,000, maybe 100,000. Okay, so here's what I get out of this. I get 0.16541, 0.45874, 0.49576, 0.49958, 0.49996. Okay, I believe those are right. So as x gets bigger and bigger and bigger, can we see the y value approaching something very specific? Well, it should be obvious that it's approaching 0.5. So we would say that the answer to this is 0.5. Okay, that seems reasonable according to the table. Now we can look at the graph if we want. So if you go to your graph with a normal window, it's going to be hard to tell because you have a window from -10 to 10. So what if I change my window to be, for my x minimum, to maybe be -10, but my x maximum, maybe I change it to be, I'll change it to be 10,000. And then I go ahead and graph it, and I can see that it kind of does this little blip, and then it goes above the x-axis and so on. So it's a little hard to see, but we can see that it's not really just growing. It's kind of flattening out in a sense. But how can we show this analytically? So we tried a table. The table produced an answer of what appears to be 0.5, and looks like I did everything right, so that's good. Now, we can infer, which means we don't know, which means we haven't proven it, that the answer is 0.5. But how could I prove this? How could I prove this? Well, here's another little trick to taking limits, and this limit only, or this little trick only applies when you are taking the limit as x approaches infinity or negative infinity. And sometimes this doesn't work, but when nothing else works, you try this, okay? How can we show this analytically? Well, go ahead and write this down, and this may be a little confusing the way it's worded, but you'll see what I mean when I do it. Reduce the fraction by its highest power. So what's the highest power in this expression? The highest power is 2. It's squared. So we are going to reduce this by x squared in a sense. And what I mean by that is I am going to multiply the top by 1 over x squared and the bottom by 1 over x squared. Okay, so I'm going to multiply this by 1 over x squared. Now, it seems like, why are you doing this? But you'll see that it does actually produce an answer in the end. Why is it 1 over x squared? Because the highest power is squared. So now let's go ahead and do this. And why do I have to do it to the top and bottom? Well, because I don't want to change the meaning of this per se. I just want to change the way it looks. And so I'm changing the way it looks because all I'm really doing is multiplying by 1, right? This is 1. So I'm just changing the way it looks, not changing its values. So when I multiply by x squared, I get limit as x approaches infinity. I got to distribute this in. So what's x squared times 1 over x squared? Well, that's 1. What is negative 5x? Let me go ahead and write this out. It would be x squared over x squared for the first one. The next one would be minus 5x over x squared. The next one would be minus 6 over x squared. So that's the top. And the bottom would be 2x squared over x squared plus 7x over x squared minus 4 over x squared. Okay, so we have this expression now. You can hopefully see now that you can reduce a bunch of things individually, like x squared over x squared is 1. So limit as x approaches infinity of 1 minus, well, one of those x's reduced, so you're 5 over x, minus, well, that doesn't reduce at all, so we're going to leave that there. And then in the bottom, 2x squared over x squared is 2, plus this one, the x is 1x reduces, so 7 over x, and then that one stays the same. And so we end up with that expression. You go, well, I don't know what that does, but now, since I reduced something, there might be something that happened. Well, let's go ahead and try substituting again. This would become 1 minus 5 over infinity minus 6 over infinity squared. Let me put parentheses around these. Over 2 plus 7 over infinity minus 4 over infinity squared. Okay? Now, maybe this rings a bell because I said you really want to make sure you know these things. Remember, when you have an infinity on top and a constant on the bottom, the answer should be infinity. When you have a constant on top and an infinity on the bottom, you should get 0. As the denominator gets bigger, the answer gets smaller, 0. So look what we have here. We have a constant on top and an infinity on the bottom. So this becomes 1 minus 0. 6 over infinity squared. Well, infinity squared is infinity. 6 over infinity is 0. All over 2 plus 7 over infinity is 0. Minus 4, infinity squared is infinity. 4 over infinity is 0. And we can see 1 minus 0 is 1. 2 plus 0 minus 0 is 2. And our answer is 1/2. That's pretty cool stuff, huh? So that's the analytical approach to figuring out some limits as x approaches infinity. Remember the process. Always substitute first. If you have x approaches infinity or negative infinity, then after you substitute, you can go straight to dividing by the highest power. Otherwise, you might try factoring or conjugates or something like that. But notice, I'm just trying to algebraically manipulate this so it appears differently than it originally started with, so that it might produce an answer that I understand, okay? So that's exactly what I got here for my example. So here's a practice problem for you. I want you to go ahead and try doing this and see what you come up with, and then come back and push play and see how you did. All right, for this problem, we got the limit as x approaches, negative infinity of 8x to the 4th plus 3x cubed plus x all over 2x to the 4th minus 4x plus 7. All right, first step is substitution. And I'm going to kind of skip this step. Not that I'm skipping it in my mind, I'm just skipping it on paper. You should not do that. Infinity, really big infinity, really big infinity, really big infinity, adding them all up, got infinity on top. Really big infinity minus a smaller infinity, because that's a power, so that's still infinity, plus 7 is infinity. Infinity over infinity is indeterminate. So because this is a limit as x approaches negative infinity, I'm going to go ahead and divide by the highest power, or another way of viewing that. Now, I know I did this. The highest power here is to the 4th, so you would do 1 over x to the 4th and 1 over x to the 4th, right? Another way to view that is to say, that's the same as saying divide by x to the 4th, divide by x to the 4th, essentially. Okay, it's just a little quicker. So when I go to do that, I'm going to kind of skip some steps. I'm going to reduce things as I go along. 8x to the 4th divided by x to the 4th is 8. 3x to the 3rd divided by x to the 4th is 3 over x. And then x over x to the 4th is 1 over x cubed. And then the bottom, the x to the 4th is reduced, so you got 2 minus 4 over x cubed. I think I yeah, that's right, plus 7 over x to the 4th. Okay, so there I rewrote it in a different way, and then I'm going to go ahead and substitute now. So the limit, oops, don't need to put limit because I'm substituting. 8 plus 3 over negative infinity plus 1 over negative infinity cubed over 2 minus 4 over negative infinity cubed plus 7 over negative infinity to the 4th. Okay, so this is simple enough. 8. What is 3 divided by infinity? It's 0. What's a positive divided by a negative? It's a negative, so it'd actually be minus 0. What's negative infinity cubed? It's negative infinity. 1 over infinity is 0 with that negative, so it's minus 0 again. Bottom, you got 2. The bottom here, this numerator is negative infinity. So negative 4 divided by negative infinity is plus 0. And then negative infinity to the 4th is positive infinity. 7 over positive infinity is plus 0. And so you can see all that goes away. You got 8 over 2, which is 4 as our final answer for our limit. So that's pretty cool stuff. I think that is a convenient way to deal with some limits analytically, especially the infinity and negative infinities. All right, let's go ahead and talk about how this applies. What does this matter? Well, I referenced this earlier on in the lesson, that the actual definition of a horizontal asymptote is the limit as x approaches infinity and negative infinity. The idea is this. If I have a function that does something, let's say, does something like this, okay? You can see this is kind of a exponential function of some sorts. We can see that we have a horizontal asymptote here, right? It looks like it's flattening out and it's going towards something. The reality is that this, the limit as x approaches infinity, as we get further and further and further out this way of the function, is 0. Okay? So that's the definition of a horizontal asymptote. That it, as the limit as x approaches infinity or negative infinity of a function approaches a specific number. And so I'll give you another graph real fast so you can see this. And we're going to explore this a little bit more too. Let's say that I have something that looks like this, another exponential function, maybe a normal one. And then we would say, okay, is there any asymptotes here? It doesn't appear to have an asymptote on this side, but it appears to have one on this side. Well, what are we taking the limit? We're taking the limit as x approaches negative infinity of our function. And that looks like it's approaching a specific number, whatever that is. And so let's say that's negative 4 there. So the limit as x approaches negative infinity is negative 4. And we'd say, therefore, f of x has a horizontal asymptote of y equals negative 4. It's a y value. Okay? So that's what an asymptote actually is. Let's see here. Here's another graph. The picture that I gave you actually has 2 horizontal asymptotes. You have the idea that this function is flat, and then it kind of goes up, and then it kind of goes back down. You've seen a couple functions like this in the past. But you can see that, let me go ahead and bring this up. The limit as x approaches negative infinity, so as x approaches negative infinity, as we go this way, negative infinity, we can see that it's approaching negative 3. Okay? And the limit as x approaches positive infinity is approaching positive 3. Because the limit as x approaches plus or minus infinity, either one, gives you a specific number, then you have a horizontal asymptote at that number. Okay? So therefore, f of x has a horizontal asymptote of y equals negative 3 and y equals 3. So let's go ahead and take a look at an example of this, because this is an important problem. Determine the horizontal asymptotes. And I get so many students that they just get lost. They read that problem and they go, I don't know what to do with it. That's nothing that we've done. You haven't given us any practice with this. It comes up on a quiz or a test and you go, I don't know what to do. Well, go back to the last slide and read the definition. How do I find horizontal asymptotes? It's the limit as x approaches plus or minus infinity. So let's take the limit as x approaches plus or minus infinity. And if we get numeric answers, then we will have an asymptote. So h of x equals 5x cubed plus 4 over x cubed for x is less than 0, and negative x minus 6 over 2x squared plus 1 for x is greater than or equal to 0. So we have a piecewise function here. And it says determine the asymptotes. So in order to find the horizontal asymptote, you take the limit as x approaches infinity and the limit as x approaches negative infinity. Okay, so if you get a numeric answer out of either of these, then you have a horizontal asymptote there. That's the definition. I didn't put an argument in here because I want to figure out which one I'm going to use. I don't want to use both necessarily. The limit as x approaches infinity, the limit as x approaches infinity, I wouldn't use this top part because this domain is negative numbers. I want positive infinity, so I'm going to use this bottom one. So that's negative x minus 6 over 2x squared plus 1. On the negative infinity, I am going to use the top one because that's dealing with the negative interval. So it's 5x cubed plus 4 over x cubed. And so remember, the first step is always to try substitution. We have negative infinity minus 6 over 2 times negative infinity squared plus 1. Well, negative infinity minus 6 is negative infinity. Negative infinity squared is positive infinity. Times 2 is positive infinity plus 1 is positive infinity. So we have an indeterminate form. So we have to try something else. Remember, anytime you're dealing with infinity or negative infinity, you could always try dividing by the highest power. Well, what's the highest power here? The highest power is squared. So I'm going to divide by x squared on both of those. So we got the limit as x approaches infinity of negative x over x squared is negative 1 over x, negative 6 over x squared. And then the other one, 2x squared over x squared is 2 plus 1 over x squared. And then from here we'll substitute, so we end up with negative 1 over infinity minus 6 over infinity squared all over 2 plus 1 over infinity squared. Remember, anything over infinity is 0, so that would actually be negative 0, if you would, negative divided by positive. That would be negative 0 as well. You got 2 on the bottom plus 0, so we got 0 over 2 or just 0. Okay, so that's one limit. Let's try this one now. We'll try substitution. So it's going to be 5 times negative infinity cubed plus 4 over negative infinity cubed. Negative infinity cubed is negative infinity. Times 5 is negative infinity plus 4 is negative infinity over negative infinity. It's indeterminate, so we're going to try something else. Because it's infinity or negative infinity, we're going to divide by the highest power. So the highest power in this case is x cubed. And so we end up with the limit as x approaches negative infinity of 5 plus 4 over x cubed all over 1, right? And then plugging that in, 5 plus 4 over negative infinity cubed all over 1. So we get 5 plus, well, that's negative infinity. 4 over negative infinity is 0, so it'll be minus 0 because a positive divided by negative all over 1. And so our answer is 5. Oops, I don't want to box that because that's not my final answer. So we have our two limits. Because this limit as x approaches infinity is 0, that's a numeric value, we could say there are horizontal asymptotes of y equals 0. And because this one produced a numeric answer, that's also an asymptote. So if you were to graph this on Desmos or your calculator or something like that, you would get a piecewise function, and you would see the negative infinity, this one, whatever it's doing, it might be going down like this or might be going up like this, but it's approaching 5, right? And then on this one, it's approaching 0. So as x approaches infinity, it's going to 0. So this one's going to 0, this one's going to 5, so there might be a gap in between there or something along that line. So that's the idea, that's the application of these limits as x approaches infinity or negative infinity. Do not forget the definition of a horizontal asymptote. That is so important for you, okay? So we have horizontal asymptotes at those two places. Let's go ahead and do, actually before we do this exit problem, I do want to talk about the idea of asymptote because there's a misunderstanding with students in terms of what an asymptote is. An asymptote in students' minds is a line that a function cannot cross. And that is not true. We think that maybe this guy has a horizontal asymptote because it never crosses that line, that dotted red line. But that's not the reason it's a horizontal asymptote. The reason is because as x gets bigger and bigger and bigger, we're approaching a very specific number that is equivalent to that red dot or red dotted line. But what about a function that looks like this? Let's say it goes up and then down, something like that. Well, is there a horizontal asymptote? What is x, as x approaches infinity, it looks like it's flattening out. So that looks like it could be a horizontal asymptote. Let's call this number 2. We would say the limit as x approaches infinity, right here, as it goes further and further out there, of f of x is 2. Because of that, we have a horizontal asymptote of y equals 2. But Mr. Bunye, the function crosses through the line. It's okay. I don't know where you got in your mind that it's not okay. It is okay as long as it's approaching a specific value. You can have the function cross through a line an infinite set of times and still have a horizontal asymptote. I think what happens is that students get confused with horizontal asymptotes and vertical asymptotes. Because you see, if a function crossed over a vertical asymptote and then approached that vertical asymptote, you would have a problem because it would have to come back on itself, which means it's not a function. So you can't cross over a vertical asymptote because then you don't have a function. But you can cross over a horizontal asymptote because it's still a function. All right, with that said, we have an exit problem here. We're going to kind of go fast through this. We're looking for the limit as x approaches negative infinity of this function. We're not looking, x approaches negative 3. We're not looking at infinity or negative infinity, so we're not going to divide by the highest power. We could try substitution. It's not going to work. That is indeterminate. So we are going to multiply by the conjugate. Rad x plus 7 plus 2 over rad x plus 7 plus 2. We're going to multiply the top and simplify that to x plus 7 minus 4. The bottom we're going to leave the same, and then the top simplifies to x plus 3, and then we have a factor of x plus 3 on the bottom, so we're left with 1 over rad x plus 7 plus 2, and then when we plug in negative 3, we can simplify that to be 1 over 4 as our final answer. So that is the end of this lesson. If you have any questions for me, please feel free to reach out. I hope you kind of have this spark in you that maybe grew because of the idea of talking about infinities and dividing by infinity and all, and why is the number getting smaller when you're dividing by a big number and all that. It's kind of cool stuff. But if you have any questions, reach out to me and I will talk to you later.